Okay, so let us get back to the equation that we left with in the previous lecture. So, this is the del T over del x at x equal to 0 and this is the form of the equation. Now, if we want the heat flow rate which is Q over A at x equal to 0, that is the heat going in from the solid into the mold, that is what Q over A at x equal to 0 means. So, this Q over A at x equal to 0 turns out to be, and since alpha m also has the Km factor and other rho m Cm, so we will break it into those smaller ones which is Km by rho m Cm into T into pi times Tm minus T naught. So, this becomes root so this is our Q over A heat flow rate into the mold at the interface. We have invoked, remember we have invoked x equal to 0. If we had not invoked x equal to 0, then it would have been valid throughout the mold, that equation of del T over del x, but we invoked x equal to 0 to get to this equation, because you will see we will get something substantial out of it. So, this is our equation that will carry forward from here. This is the heat flow rate. Now, that is one form of heat flow rate. We can also get Q over A in another or you can say using another logic. What is actually heat flow rate? That is going into the interface. If you think about it, what it is whatever small layer of the liquid that solidifies. So, let us say this is the liquid that solidifies in time, some time del T. So, this is the del S length that has been formed, or del S in time del T. Now, whenever this solid forms, some amount of heat is released. What is that heat? It is heat of fusion. So, depending upon the amount of solid liquid that has solidified, that will be the equivalent amount of heat that is released, and therefore, Q over A can also be written as meaning in del T this del S length has solidified, and proportional to that whatever is the amount of heat that has been generated, because when the liquid solidifies, then some amount of heat is released. So, whatever heat has been released is what is being transferred all the way from the liquid to the solid to the mold. So, that is the real Q over A, or the heat actually that is going in. So, now you see we have Q over A at x equal to 0 in this form and Q over A at x equal to 0 in this form. So, we can equate these two and get a equation something like this. And if you want to find what is the length that has solidified as a function of time t, all you need to do is integrate this equation with respect to t. So, integrating with respect to time you can show that, or you can easily see or obtain from this equation that S will be equal to square root of t. So, this S, the length that has solidified, can be obtained in terms of this time t. This is proportional to square root of t. Not only that, there are few more things. We see that it is it is dependent on metal properties. So, these are the metal properties, the rho s, which is the density, Tm and T naught. Tm is actually the melting point of the solid, H is the heat of fusion, and these are the thermal properties of the mold. Note how that Km, Ks etc. have not come into the picture. Why? Because we have assumed that conductivity of mold is so small that it will only play the role of or that will be the limiting condition that will determine the rate of solidification, and that is what we are actually getting. So, you see that S is dependent on Km, but not on Ks. Similarly, it is dependent on Cm, but not on Cs. But overall, that is the form of the equation, S or the length of solidification as a function of time t. Now, this as you can clearly see that S is dependent both on metal properties, not exactly the conductivity and specific heat, but still some of the metal properties, and on some thermal properties of the mold. Therefore, if you change the metal or the mold, you would be getting different curves. So, if we let us say you plotted S as a function of root t, what would you expect? You would expect a straight line. Let me draw it again to show that it is indeed a straight line. It is a schematic. So, this is a straight line that you would obtain because S is a proportional to root t, and all other parameters over there in that equation are fixed or they are material properties. Now, if let us say this, we say that this is for one particular material which is magnesium, or one particular combination of metal and mold. So, magnesium in sand. So, it will come out like this. Now, let us say if I change the metal, but keep the same mold material, you may get a different curve, and these are just schematic. I am not trying to say which one is has higher conductivity and lower conductivity. This is just to show that it will remain a straight line, but it will still be dependent on what combination of metal and mold material you select. So, for example, this can be copper in sand, and this time let us keep the metal constant and change the mold material. So, let us say we have copper in plaster. So, you see you get straight line curves, meaning S will always be proportional to root t, but it is still change depending on what is the metal and mold combination. So, this is our insulating mold condition. Now, just a last bit of knowledge that we need to look into when we are talking about insulating mold condition. So, what kind of materials we said, or what kind of metal mold combination this would be suitable for? We said that it is insulating mold. So, this will be suitable when you have like we said earlier at the beginning, for a highly conductive metal and a very insulating mold. So, for example, if you are talking about aluminum, copper in sand, or even magnesium. So, this will be these equation will be accurately predict for some combination like this, magnesium, aluminum, which are high conducting materials, but in a insulating mold like sand. But if you are talking about let us say aluminum in steel, you do have a permanent mold casting. So, aluminum is very conductive, true, but steel is not orders of magnitude different from aluminum. So, in that case, mold material, which is the steel in this case, will not act like a insulating condition, and therefore, these equation not true or not accurate. It may be combinations like aluminum in steel, because steel is not very different in conductivity. It is smaller than conductivity of aluminum, but not by several orders of magnitude. Similarly, steel in sand, steel is low in conductivity and sand is not so bad, but so they are again not orders, not several orders of magnitude different. So again, steel in sand is not a good combination that can be predicted using this insulating mold condition. Okay, I said this is the last bit of thing, but actually I missed one more thing. We have another important thing that we can get from here, which is what is called as the Chvorinov's principle, which is to find out what will be the total time for solidification. And again, what we need is equation that we have already obtained, which is S equal to 2 over root pi Tm minus T naught by rho sh times Km rho m Cm root T. So now what is how do we get to that? Remember, we said that these equations are being derived for one dimensional objects. So for example, a rod, very thin rod, if you are looking, and we were looking at the solidification of this, then it is as good as so this is solid, this is liquid, and then you can say, okay, this equation was valid. But what will change if we are talking about some simple geometry but 3-dimensional, let's say a cuboid? The heat flow directions do not change by much, because these are still simple geometry. So if this was the solid part, this was the liquid part, still the heat flow directions remain similar as we had in a one-dimensional rod. And therefore, these equations, the equation that we obtained for 1D can be easily extended to simple 2D and 3D geometry. Okay, so although we derived it for 1D, like I said, but if the geometry is very simple like these, we can easily extend that equation, which was our all the equations that we described about. For example, our S as a function of t and q over a and del t over del x, all those things would be equally valid for these simple geometries. Now what will be different when we are talking about a little bit more complex geometry? Let's say if we are talking about a geometry where there are convex shapes, this is the way heat is going in, or concave geometries. So this is the liquid part, this is the solid part, here this is the liquid part, this is the solid part. These are two different conditions we are talking about. So what you see is changing here is that here the heat is converging, over here the heat is diverging. So yes, there is some amount of difference, and because the heat is diverging, it is no more one dimensional like what we assumed earlier for the previous case. It becomes 2-dimensional at the least, and even 3-dimensional depending on if it has curvature in the third direction, that is the z direction. So these things can cause a difference to the solidification time, the total length that we have talked about, S as a function of t. But let's assume that we are talking about simple geometries like these, then we can replace this S by V over A. V is the total volume, and A is the metal mold interface area. So if we talk about S is the total length. As you see, if you keep going all the way out to the end, then this becomes your whole volume, which is the total volume that has solidified, and this is the interface area. So this interface area remains almost constant, and therefore in simple geometry it will always remain constant. So under that assumption that the heat flow per unit area remains constant, we can say that S will be equal to V over A, which is the S that we obtained here, but in the final time, that is when the complete solidification has taken place, just at the point where complete solidification has taken place. So at that point S can be said as V divided by A. So see, the dimensions are the same, and at the same time V over A, if as far as simple geometries are concerned, it remains the same quantity as what we derived earlier. And this will also imply that T will have to be equal to Tf. So it is not a variable anymore, it is a total time that has been taken for solidification. So now you can replace these over here, and we can get where V is the total volume we are talking about. Whatever is the total volume of the cast that has been solidified, A is the metal surface contact area, the metal mold contact area. So V over A will be proportional to Tf, or in other words, let me erase this part to write what will be called as the Chvorinov's equation. So this is what is called as Chvorinov's rule or equation. This is giving you the total time that will take for solidification in terms of the volume and the area, contact area of metal and mold. So Tf is proportional to square of V over A, and C is a constant. You can get C from this for simple geometries, and in fact even if the geometry is not very simple, you can obtain a C for that particular kind of geometry and still get a relation like this, where Tf is equal to C times V over A square. So if you were to plot this as log T you will get a straight line again. So this is volume by area ratio for different molds for the same metal mold combination, and the total time it takes. You plot the log plot of this these values, and you will get a straight line, which shows that Chvorinov's rule is valid, and it holds true for this whenever you have insulating mold condition. And remember what were the insulating mold condition? When you have aluminum and copper, or a copper in say sand mold, or even magnesium, any other conducting material like those, but not something like aluminum in steel or steel in sand cast mold. So those will not aluminum in steel or steel in sand cast will not be considered as insulating mold. Okay, so at one point of time earlier we talked about the form of the curve that we see, the temperature profile that we see, and we said that we will look back into it later on. So now is the time, because we are again and again plotting it, and even before we move on without getting into the proper understanding, let us have a look and try to understand. So this is your mold, this is a liquid, this is a solid, and not in let us say we are talking about some condition where there is also temperature drop in solid, but there is no interface resistance. Again we are just trying to understand why the plot look like these. That is the whole intention. You remember I said that when you go from left to right, you see a increasing slope for the mold, while when you go from left to right for solid, you see a decreasing slope for the temperature profile. So this is again temperature, this is distance. So now it is time to take a look into it. Why do we always draw it like this? You can say a concave here and a convex over here, and not the other way around. So again let us go back to our equation for the heat flow. Q over A, let us say we are talking about the heat going into the mold, which was at x equal to 0, is equal to minus Km so the heat that is going into the mold is Q over A by at x equal to 0 minus Km times del T over del x at x equal to 0. So what we want to understand is what is happening, or how is it changing when we, let us say when we go from this point to this point. Now this is a parameter, do you think that can change when we go from here to here in the mold? No, it will not. What will change is this, it is the slope or the thermal gradient. So this thermal gradient, when we go from x equal to 0 to some minus values of in the mold, we will see that this becomes smaller and smaller. So what will that mean? So if we are talking about q x equal to 0 and let us say x equal to x prime, which is lower than x equal to 0, so in here this is this quantity is larger and this quantity is smaller, and therefore this whole quantity becomes, in magnitude wise, this is smaller than this. So what does this mean? It looks like by the time this represents, remember, the total heat rate flow. So total amount of heat that went into the mold at this point is higher, and the total amount of heat that goes into this point onward is smaller. Now that is that looks like some magic is going on over here, but it is not really magic. What you have to realize here is that what was the initial condition of the mold, and let me again draw this. So this was the initial condition of the mold, that is, it was all at temperature T naught. When we say that the temperature from the heat that went into this is higher and than the heat that went into this point, what we are saying is that some amount of heat has been absorbed, and you can see the fact that the temperature profile has raised. Initially it was a flat line, now it has went up to this. What is this? This increase represents that some amount of heat has been absorbed by the mold, and that is why the total amount of heat that goes into this point, which was Q over A at x equal to 0, which in magnitude is larger than Q over A at x equal to x prime, which in magnitude is a smaller quantity. So a smaller amount of heat is coming over here, and in an insulating mold what you expect is that the length of the mold is such that by the time the outside of the mold starts to get heated up, your solidification has taken place. So that is what the semi-infinite insulating mold condition means. We will look at some more at this profile, temperature profile in for the solid part again in the next class, but for the time being just look at this part and also try to understand what is going on in the other part. In the other part, if that is the case, why is the other part showing an inverse curve? So, we will look at that in the next class. So, we will finish off over here and come back to this in the next class. Thanks.